So let's get started. For today's session, it's Introduction to Linear Regression using spreadsheets with real estate data. So what are the goals of working with real estate data? There's many goals that we might have. I'm just going to focus on two specific areas, but of course we can always think about a lot more than these. So the two goals that I'm going to offer for today is predicting prices. So this could be any of the two sides. Maybe you're trying to sell a property and you want to know what is the right price for that property, or maybe you want to buy a property and you want to know if you're paying fair market value for that. And there's a lot of factors that affect the price of that property. The second is understanding how the factors that affect the price of the property can be manipulated. So imagine that you're trying to sell a property and you have an extra $10,000 that you can invest in that property. Where should you put those $10,000? So for example, you could update the kitchen, or you can update the bathrooms, or maybe you can get a hot tub. What is the ROI of investing in each one of these different areas to really increase the value of your property? So what we're going to do today is really understand how we can make these types of predictions, and we're going to use spreadsheets. So for today, I wanted to briefly introduce myself. So my name is Roberto Rafe. And for the last 20 plus years, I've been working in as an instructor in the areas of technology, data science, and analytics. So these types of trainings is what I enjoy doing for a living. For today's agenda, I have split it up into three distinct sections. The first section is a very short one where we're going to review what the line equation is and how it works. The second section, we're going to go through the theory of linear regression, just a superficial part of it. There is a lot to understand about linear regression. We're just going to cover the beginning part of it. And then we are going to delve into spreadsheets. So towards the second half of this 1 hour workshop, we are going to be working with either Excel or Google Sheets. You can choose which tool you prefer to use, and I'll give you a data set, and we're going to work through this together. So let's get started. Let's start working with a review of what the line equation is. So here, let me see if I can change my marker into a laser pointer. Here we have an x-axis of a graph, or the horizontal line, and we have a y-axis, and we have a blue line. And this blue line is given by an equation that is y equals mx plus b. The value of x is what we have here on the horizontal side. The value of y is what we have on the vertical side. And then we have these two values, m and b. So let's review what m is. M is known as a slope, and it is given by the following equation that we see here on the right. And the way to understand what the slope is we have to pick two values in our line. It can be any two values as long as they're distinct values. And the first part is we determine what is the value of every point in the y-axis. So this one has a value of y2, the other point has a value of y1. And when we subtract these two values, we get this purple bar. And this purple line is what goes here on the numerator. Then we can do the same thing on the x-axis, where we have x2 for the first point and x1 for the other point, and we subtract them, and we get this purple line here, and that goes in the denominator. And when we take the ratio of these two numbers, that is what the slope is. It's also known as the rise over the run. And when the line is trending upwards, so if you think you're walking on a mountain going uphill, that slope m is positive. If you're walking downhill, the slope m is negative. And if you're walking flat, that slope m is equal to 0. So I'm going to pause for a minute, and I'm going to ask you if you can put in the chat, do you feel I'm going too fast? Just type the word fast. If I'm going too slow, type the word slow. And if it's just right, just type in the chat just right so I know how things are working. All right, I see the chat a little bit quiet, but it's a little too slow. Okay, I can speed things up a little bit, just right for a few, good for a few. Okay. Thank you for your comments. So we have determined the slope m. Now we want to determine what is the other value here, the value of b. So let's go to the next slide. And this value of b is known as the intercept. And what the intercept tells us is that on the x-axis, when you have a value of x equal to 0, what is the value of the line? And this is going to be very relevant as we build our own models. So today, I said in this hour, we're going to cover 3 sides of the agenda. The first is a review of the line equation. We just finished that. And we're going to move to the second part of the agenda, which is understanding what a simple linear regression is. So to understand this, let's start with a data set. So in this graph that I have here, on the x-axis, we have the years of work experience. So how many years has somebody been working at a given company, for example? And on the y-axis, we have their salary. And every dot in our data set is one person who works at a company. So for example, this individual has been working for 4 years and their salary would be $25,000. The question is, can we predict or can we build a model that allows us to know for any given year of work experience what should be their salary? Now we can notice that not every data point lies perfectly on a straight line. They're a little bit above or below the straight line. And this is the reason for this is because years of work experience is not the only metric we use to determine somebody's salary. It is one of them, but there's other things like what is their performance, what type of job they have, etc. But for now, let's just work on this one simple metric of years of work experience. So the question I have for everybody is, which line best fits the data? So I'm going to present 2 lines, as you can see here. One is the purple line that has a positive slope, and one is a red line that has a negative slope. And what I would like you all to do is to type in the chat, which color line do you think best fits the data? And maybe type in a word or a sentence of why do you think the purple or the red line best fits the data. So please take a minute and type in the chat. Okay, I'm seeing purple. Let's see what are other thoughts. And if you have an explanation, a brief explanation of why do you think it's the purple or the red, if you believe it's the red. Okay, because it has a positive slope. Great, that's a great answer. It is closest to the dots. That's one of the explanations. It's trending up. Great, I appreciate all your comments. And I'm going to agree with what you're all saying. So the purple line, in my view, seems to be the one that best fits the data. And you know, the explanation, at least as a starting point, is because it just looks good, right? Because I see sort of the points trending up, and this line is trending up as well. So it makes quite a lot of sense. Now, this is a visual way or a qualitative way of saying, well, purple looks better than red. But can we do it in a quantitative way? So can we figure out a metric or a math expression, if you will, that will tell us absolutely with 100% certainty that the purple is much better than the red? Now, there's a lot of metrics out there that you could use. For today, I'm just going to explain one of them. And this one is called the root mean squared error, or RMSE. And I'm presenting the equation here. And I'm going to walk one by one through all the components of this expression. So let's start using the purple line and see what we have here. The first part of the equation says y sub I minus y sub I hat. So what does that mean? Y sub I means that the I is for a given data point. So this is data point 1, data point 2, data point 3, etc. So this would be Y sub 1. The value in the Y axis for this person, that's the Y sub I. And the Y sub I with the little hat is the same value in X, but on the Y value of the line. So you can see that there's a difference between the data point and the line. And when we subtract those, we get this little purple bar. And we can do this for each one of the data points. So some bars are longer, some are shorter. And once we have that, the expression says, well, let's square those values. So if I square those values, I can convert each one of those lines into a square, and I move them all here to the left side of the chart. Now I can do the same thing with the red line. So you can see that there is a difference between the data point on the y-axis and where the line is. And that difference, I can now square it and move it here all the way to the left as well. So that's the first part of the expression. The second part is I'm going to add them all up and divide them by n. N is the number of data points. So if you think carefully about this, what this means is that you're just going to get the average. I want to get the average size of the squares. So I'm going to get the average of all the purples and the average of all the reds. And when I do that, let's say that this is the average of the purples, this is the average of the reds. Now I have one more step to do, which is I'm going to take the square root of that average. And basically taking the square root is converting the whole square back into a line. And then I can ask myself, which of these lines is the smallest one? And we can all appreciate that the purple line is smaller than the red line. Therefore, the purple one has the smallest root mean squared error. Therefore, it is the best fit to the data. So between the purple and the red, I can pick the purple because the root mean squared error is the smallest. So I want to take a quick review on the chat. How are we doing with the pace? Give me a thumbs up if things are going well, and if it's going too fast, give me a thumbs down, or if it's going too slow. All right, any thoughts on the chat? All right, we'll keep going. For the next part, so now we have determined that between these two lines, we can pick the best one, which is the purple. But are there only two possible lines to play with? And the reality is no, there could be an infinite number of lines we can play with. So what I'm going to do next is explain how we can fit to the data. So what this means is we have our equation, we have a line here, but in reality, we can play with the values of m and b. So we could have an infinite number of lines to test. So if we have an infinite number of lines and we start calculating the RMSE for each infinite lines, it's going to take us forever. So is there a better way of doing that? And the answer is there is. We're lucky that there is, and I'm going to mention them, but for this session, we don't need to understand exactly how it works, just know that they exist. So what are these ways? One is known as the ordinary least squares, and I'm showing the expression here on the left, which is a bunch of matrix multiplications where you have x for all the values of x in your data point, and you have y for all the values of y in your data points. And the result is this b vector that contains the value of m and b. And this is used for small data sets. Again, you don't need to right now understand how this works. Just know that there's a way of doing this. And all the tools like Excel, Google Sheets, Python, etc., they have this implemented underneath the hood, and we're going to use that to be able to figure out the best m and b that fits to our data. Next, on the right-hand side, I'm also going to mention there are other methods like gradient descent that comes with a lot of flavors. And this is what we know as an optimization algorithm, and this works better for larger data sets. Again, just be aware that these exist and that the tools that we use already have these implemented. So the final thing I want to cover in the theory before we move into our spreadsheets is multiple linear regression. So far we have learned about simple linear regression, which basically means we have one variable. In our case, it is the years of work experience. And with that one variable, we determine the salary. And we had our equation of y equals mx plus b. I added a sub a. So the sub a means the years of work experience. But I can add other variables. For example, what were their academic grades when they graduated college? And maybe that correlates with their salary. So notice I added a third dimension here. And in my equation, I added another mx. So I have the mx for the years of work experience. Now I have an mx with a sub b for the academic grades. And I can keep adding to that. So for example, I can see what their review was last year or information about the type of work that they do, etc. So if I keep adding that, it's going to be very hard to create a chart because now it's more than 3 dimensions. But mathematically, I can make it work and create a good model that is going to predict what the salary of an employee is based on the years of work experience, their academic grades, and other factors. All right. So we have covered now the second part of our agenda. And what I want to do next is I want to go into the spreadsheet model. So this is where we can all work together. And what I'm going to put on the screen, and I'm also going to share on the chat, are 2 links. If you plan to work with Excel for this session, here's the link. And if you plan on working with Google Sheets, you have the link down here. If you're using Google Sheets, please click on File and make a copy. If you click just on the link, it's going to be a view only, and you won't be able to edit that. So you're going to have to make your own copy to work through it. And I'm going to also add this into the chat. And what I'm going to ask everybody to do is please type in the chat if you're going to use Excel or Google Sheets. So if you can share that information, Excel. Okay, it seems that most of you are in Excel, so I'm okay. I see one with Google Sheets. Given that the majority seems to be in Excel, I'm going to do the demo in Excel. Google Sheets, you can follow along. It's very, very similar. So there's just going to be some small nuances between one and the other. All right, so I'm going to open my version, which is going to be in Excel. And can somebody give me a little thumbs up if you can see the Excel spreadsheet in my computer? Okay, can somebody give me a little confirmation that you can see the spreadsheet? Great, okay. Thank you, everybody. So let's move to the most exciting part. Here, we're now gonna implement linear regression with real estate data. So let me walk you through what I'm showing here. So hopefully you all have been able to download your Excel spreadsheet. And if you have the Google Sheets, just as a reminder, you need to make your own copy. And let's understand the data. So the first thing, you see several rows. Every row is a property that has been sold. These are real properties. Okay, somebody mentioned there's a little delay. Great, thank you for clarifying that. These are real properties. And each one of these is a property that was sold in the city of Seattle, Washington, between February and March of 2023. So these are real properties. For example, we have this property over here, and now we can look at the columns. This property was built in 1951. It has 2 bathrooms and it has 2,080 square feet, and it was sold between February and March of last year for $1.2 million. Now we have 4 columns here that we are going to be using today. I'm not going to explain what they are quite yet, so let's pause on that. And then we have other information just as a reference, like the date that the property was sold, so on February 24 of last year. You also have a link of the URL listing. So this is what we have here. And let's explore our data a little bit. So the first thing I want to do is I want to add filters to my table so I can play with it. The way to add filters is just select anywhere on the table. So I'm selecting, for example, this first cell. And I'm going to use, I have a Mac machine, so I use Command A, but if you have a Windows machine, use Control A. So when I type in Command A, it selects my whole table. And once it selects my whole table, I'm going to go into Data here at the top and Filter. So again, select a cell in your data, click on Command A or Control A, depending on whether you use Mac or Windows. Go into the Data tab and click on Filter. And what that does, if we scroll here to the top, is that it adds these triangles here so we can filter our data. So the first thing I want to show is, let's see what our least expensive property looks like. So I'm going to go into our price column, and I'm going to sort this ascending. So ascending means from the smallest value to the largest value. So now we can see our most inexpensive property was 255. Let's look at our second most inexpensive. So this one was built in 1961. It has one bathroom, 600 square foot. It was sold for $265,000. And let's click on this link to see what this property looks like. So let me bring this property here. You can see over here. And this is the information that you can see on the website. So in effect, it says that it was sold for $265,000. This company predicts that if you were to sell this property today, this would be the actual price. Notice that it doesn't have any bedrooms, so it's a studio apartment. It has one bathroom, 600 square footage, and you can see a lot of pieces of information. For example, it has a nice view to the Space Needle. We can look at some of the pictures, so you can see that the kitchen and the bathroom seem to be fairly new. It has some amenities like a swimming pool, it has a gym, it has parking, it seems to have a shared laundry room, so you don't have it inside the property, etc. So all these things are going to make the price of the property go either up or down depending on what these features are. We're not going to cover all those features today, but we will cover a handful of them, specifically the year built, the number of bathrooms, and the square footage. So now we have seen the least expensive property. Let's see what the most expensive property is going to look like. So again, I'm going to change the sorting order to descending. And when I do this, now we can see our most expensive property was built in 1925. And this property has 3.5 bathrooms, 2,800 square footage, and it sold for $2.6 million. So again, let's bring the listing here so we can see what that property looks like. And we can see that this is much different from what we saw before. Notice that this one sold last year for 2.6 million, but it is predicted to sell for even less if we were to sell it today. 4 bedrooms, 3.5 bathrooms, 2,800 square feet. And you can see what this property contains. So it has a backyard, the kitchen looks nice, etc. So it's a very different property than the one we saw before. So let's close this. Okay. So the next thing I want to do is I want to do a little bit of exploratory data analysis and just understand what my data set is telling me. So here at the top, we have this bar, this grouping bar, and I'm going to apply it on the first one. And what this is going to do is it's going to hide or unhide my columns. So if I click on it, notice that some columns are hidden. If I click on it again, they appear again. I'm just using this for space, so you can click and unclick. And the reason I want to hide them is now I want to work with this next table that I see here. So I'm going to be doing some analysis here. And some of the questions I might have is how many properties I have in my data set. So for this, I can use something like the count function. So I type in count parentheses, and I can select, for example, my price column. So that's all of column D. And when I close the parentheses and click enter, this counts only the numerical values. So it doesn't count this price row, it just counts all the numerical values. And it's telling me that I have 300 properties in my data set. The next thing is, what is the minimum price? So for the minimum, I can use my min function, so min. And again, I'm gonna select the whole column of price, close the parentheses, and it says 255,000. So we already knew that, but if we hadn't sorted the data, this is a way of finding out. We can also look at the max. So that's using the equal max function parentheses. We're gonna select again the price, close the parentheses, and this is 2.6 million. And then we can look at the average price. So we're gonna use the average function, and this is 870,000. And we can also look at the median. So what the median is telling us is half the properties cost less and half the properties cost more than this value of 775,000. Notice that the average and the median do not agree. And the reason for that is because if they were to agree, that means that there's no outliers in our data set. But the fact that they don't agree, this tells me that there's some properties that are extremely expensive that are probably pulling our average to a higher price. So those are just bits of information. Now, when you work with this data, one of the things you want to make sure is to understand that you can trust this data. So what are some of the sanity check questions you might ask yourself? So for example, if you have a year built and you have a data point that says that the year built was 10 million years ago, you would probably not trust that that property is real, right? You probably don't expect to have a property built 10 million years ago. So you want to test the boundaries. Similarly with the number of bathrooms, the square footage, and the price. So I have done some exploratory data analysis already, so I'm gonna bring this to the minimum bath. So please put in the chat, what would you expect to be the minimum number of bathrooms in a data set of home prices? So how many bathrooms would you expect to be the minimum? So please type it in the chat. So I think given that there's a little bit of a delay, I'm gonna wait a minute or so. Okay, I see somebody saying 1 bathroom should be the minimum. Okay, I see a lot of people saying 1 bathroom. Somebody put 0.5 with a question mark. Okay, that's a great question. Okay, you have 1. Okay, I think everybody is converging around the 1 bathroom minimum. And to be honest, that's what I would have expected as well. Okay, so I'm going to type in equal min, and let's look at the number of bathrooms. So I'm going to close the parentheses, and it says there's a property with 0.5, and some of you put 0.5 as an option. And you know, it piqued my attention, right? Because I said, what does that mean? Does that mean I'm going to live in a house that only has a sink and a toilet, and it's not going to have a shower? I mean, maybe. So I got curious. So I said, okay, let's look at this property of 0.5. So now I'm going to sort my data from bathrooms ascending, and here's my famous 0.5 bathroom property. And let's expand and click on the link so we can actually see the listing. And let me bring the listing here. So this is our famous property that has half a bathroom. So let's look at it. It has 2 bedrooms, and we can see in effect it says half a bathroom. So I was curious how this works. So then I decided, okay, let's look at the pictures. And here you can see this nice property, and here you can see this is my half bathroom. This makes sense. It has the toilet, it has the sink. I don't see a shower. But then I keep scrolling down, and suddenly I see a picture like this one. And here's a sink, here's a toilet, here's a shower. So clearly to me, this property has a mistake, because at least I can count 1.5 bathrooms. Maybe there are more. I don't know. But it raised a flag. And to me, this is a mistake. So this is real data. It's out there in the world, but it's clearly a mistake. So when you work with data, you want to look for these things, inconsistencies, and you want to highlight them. So you want to go in here and then say, well, this data is not correct. Go with your team who collected the data and try to find out, why is there a mistake? And is it only this property that has a mistake? Or does this mean that now all bathrooms probably have some sort of a mistake? So you want to be very cautious and careful about that, and always be skeptical. For today, we are not going to fix this. We're just going to keep it as it is. But there's a famous expression that says garbage in, garbage out. And what that means is that if your data is garbage, like this property, and you start building models with garbage data, then doesn't matter how good your models are going to be, you're not going to get good predictions because your data is incorrect. Okay, so moving on, please type in the chat, how am I doing with the pace? Is it, again, just right, too fast, or too slow? And as you do that, I'm just going to hide these columns here, and I'm going to hide, again, now these columns here, because I want to now start working with this section of our spreadsheets. So I'm going to pause for a minute as you type into the chat how the pace is going. All right, seeing a lot of good, just right, great. I appreciate for that feedback. Okay, so now let's get to the most exciting part, which is what we all came here to do, is to apply linear regression. So I'm going to work with two models. The first model is the most simplistic model you can think of. And I'm just going to use the square feet to predict the price of the house. That's it, just the square footage, no other parameters. And the second model, I'm going to use these three parameters, the year built, the bathroom, and the square footage, to predict the price. So let's start with the first one. And I'm going to show you how to do this in two ways, okay? The first way is a graphical way that you can only use when you have only one variable like square footage. So how are we going to do this? The first thing I want to do is I'm going to insert a chart. So I selected my two tables. I'm going to go into insert, and I want to insert a scatter plot. So a scatter plot is here. So I'm just going to pause for a minute so everybody can see where I'm at. So again, I select my two columns, square footage and price, insert, and I'm going to select a scatter plot here. And once I do that, this is the chart that I get. I'm going to make it a little bit bigger so we can all appreciate it. So at the bottom on the x-axis is my square footage, and on the y-axis is the price. Now, if I were to fit a line to this data, would the slope be positive, negative, or zero? Please put it in the chat. What do you think it is? All right, I'm seeing lots of positives. Okay, and I would agree. That's what I would expect. And the reason is because we can see, for example, properties that are less than 1,000 square feet tend to have prices less than $1 million, somewhere here. And more expensive properties, they have higher prices, but there's a lot of outliers. For example, here we can see a 4,000 square footage property that costs only $500,000. So let's fit a line here. So there's one way of doing graphically, and the way to do it is you select your chart, you go up here to chart design, and on the left, you have add element. And when you go to the bottom, you have this thing called trend line and linear. So I'm going to pause there and go again. You select your chart. On the top, on the ribbon, you select chart design. You go into this add chart element, trend line, and I'm going to click on linear. And what that does is that it adds this line over here. So this is a line that describes the data. So let me ask you all, if I were, according to this line, if I were to have a property that, let's say it's 3,100 square feet, so somewhere around here, what does my model predict the price of that house to be? So it's 3,100 square feet. What do you think the price should be for that house? All right, I'm gonna wait a little bit longer since there's a delay with the video. All right, so everybody is saying about 1.5 million. That's correct. So notice we have this property over here that is close to 3,100, that is not 1.5 million, and this one over here, but our model is telling us 1.5 million, 1.6, something along those lines. So you all get the idea. Now I'm gonna double click on that line, and when I double click, I open this window here on the right. And in here at the bottom, it says display equation on chart, and I'm gonna click on that. So again, I double click on the line, it opens this format trend line, and at the bottom, I'm gonna click on display equation on chart. And what this does is that it adds this equation here. I'm just gonna make the font bigger so we can all see it. Let's see if 24, okay. And this is the equation of that line. So it says y, so y is our price, equals 417x, where x is my square footage, plus $200,000. So let's interpret what this means, okay? So the first thing it's saying is it's $417 on the slope. What this is saying is that every square footage I add to my property, I can add $417 to the price. So if I have a property and I can add more square footage to it, I can add $417. So this is some feedback. If you have, let's say, a house that is one floor and you add a second floor, suddenly you double the square footage, and you can multiply that, the new square footage by 417, and that adds value to your house. Hopefully the cost of adding that second floor doesn't exceed what you are going to make in your sale. Now, the other thing you're going to notice is that if I make my square footage exactly 0, so 0 square footage, I'm selling basically nothing, then I can sell that nothing for $200,000. Obviously, that does not make any sense, but it is a model. And there's a phrase or an expression that says, all models are wrong, but some are useful. So what that means is, yeah, this model doesn't work for everything. For a 0 square footage property, you're not gonna be able to sell that for $200,000. If not, we would all be very, very rich. But for properties that, for example, our smallest one is about 300 square footage, this model starts making some sense, and we can start making predictions and so on. So far, we have been able to create a linear regression using just one variable, which is square footage, and using just this chart. I'm going to teach you how to do the same thing using functions. So for that, I have this table here at the top where I have a slope and an intercept. I want to create a model that looks like this, y equals m times square footage plus b. And I'm going to use this function called linear estimator. So linear estimator, or linest, I'm going to type in parentheses. It asks me to put the known values in y's, the known values in x, and then it has two parameters, a constant and stats. So my known values in y is my price. So I'm going to select my whole price starting from cell D2. I'm going to go all the way down and select this whole data. So I'm going to go back up. So notice it goes from D2 to D301. I'm going to add a comma, and now it's asking for all my known values in x. So for x, I'm going to go with this one here, which is C2. I'm going to type in C301. And then it asks me if I want to manipulate the constant and the stats. For now, let's type in true and false. I'm going to explain what that means in a minute. So again, equal linest parentheses D2 to D301, comma C2 to C301, and then I have a true and a false. And when I do that, it spits out two values, 417 and 200,000. Now notice the equation here is 417.08. This is 417.077. It's the same number that has been rounded. And then this one is 200,532.9, 200,533. So it's the same number that has been rounded. So I have been able to extract this value of M and B just using this linest function. Now, briefly, I want to mention these two parameters at the end. I have a true and a false. If I make this true as a false, what this does is that it forces, let's see if I typed that correctly, it forces the intercept to be 0. And in some cases, you might want to do that. This way, if I have a property with 0 square footage, it's going to sell for $0, but your model is not going to be as good with this slope. So for today, I'm going to bring this back as a true. Finally, my other parameter that has a false for the stats, if I type it as true, what this means is now in my table, I have another set of values here. And this is a bunch of error metrics that you would need to read the documentation to understand. So we're not going to cover that today, but just have it as a reference. So for now, we're going to type this as false. So now what I want to do is I want to use this first column here to make my predictions. So I want to use the equation that I have here, y equal m times square footage plus b. So let's type it in. Equals, so now I want my slope m. My slope m is this cell here that is O2. Now I'm going to make that an absolute reference. If you don't know what absolute or relative reference is, just bear with me. We're not really covering that today, and I'm happy to answer questions later. But for now, you're going to type O2, and you can click on F4 on your keyboard, and that adds these dollar signs before the O and the 2, or you can manually add the dollar signs. So that's going to lock the slope in place, and I'm going to multiply it by the square footage, which I will not lock in place. And to that, I'm going to add my intercept B, which I'm also going to make an absolute reference by clicking on F4 and adding the dollars. So when I do that, what this is telling me is this property of 1,102 square footage is predicted to sell for $660,000. Clearly, it was not accurate, but it's close enough. And I can double click here, copy this all the way down, and we can see all the different properties, and you can see the prices and the predictions, and they're somewhat close, but there's going to be an error. And the reason there's an error is because square footage is not the only parameter that allows you to predict the home price. You have to include bedrooms, bathrooms, how recently was the property renovated, etc. All right, so we have done our first model. Now I want to click over here at the top and group these cells and hide them and build my second model. Notice that my second model is going to include all of these three columns. So for this, I'm going to again type linear estimator, linest, parentheses. I'm going to select again my price. So I'm going to select all of those. And then for the known X values, I want to select all of these three. So notice what I'm typing in. I'm typing D2 to D301, comma A2 to C301. So I'm including all three columns. And then I'm going to use the true and false at the end. I'm going to click on enter. Just as a reference, the expression that I used is presented down here. And notice that now I get values for the slope and the intercept. So let's understand what this means. This model tells me that every square footage I add to the house, I increase the value by $335. Every bathroom that I add to the house increases the value by $117,000. That's a great investment. So if you have room to add another bathroom, that I would suggest you consider doing that. I also suggest you don't take the data just as is. This doesn't mean that you can go into your house and build 50 bathrooms and nothing else, and it's just a house filled with bathrooms and the property is going to sell well. So we also have to, even mathematically, this is what it is telling us. We also need to understand that that is not rationally what you would do. Finally, it says that the slope for the year built is negative, meaning that older properties cost more than newer properties. And our intercept is $988,000. What this means is that if we have a property of 0 square footage, 0 bathrooms, and was built on the year 0, this is what we could sell that property. Again, this doesn't make a lot of sense, but it is a model. So now let's build our prediction. For this, we're going to type equal, and we're going to use this expression here. So we're going to grab the slope of the square footage, use F4 to make it an absolute reference, and we're going to multiply that by our square feet. To that, we're going to add the number of bathrooms, the slope, make it an absolute reference, and multiply it by the number of bathrooms. We're going to do the same thing with the year built, make it an absolute reference, and multiply it by the year built. And finally, we're going to add our intercept and make that an absolute reference. And you can see that our prediction with this model was, for the first property, $500,000. Let's copy this all the way down. Now we have different predictions. So this property sold for 1.2, one model predicted 1.1, the other one 1.0, etc. Which model is the best between these two? For that, we're now going to use our root mean squared error equation that we have here. So remember, what we want to do is find which one has a smallest root mean squared error. So the first thing I'm going to do is I'm going to use this deviation, so actual price minus predicted price squared, and I'm going to use this column here to calculate that. So to do that, I'm going to use equal parentheses, actual price minus the prediction of the first model, and I'm going to square that value. And I'm going to do the same thing with my other model. So equal parentheses, price minus my prediction of the second model, and I'm going to square that. And I'm going to copy this all the way down. So now for both models, I have the difference between the price and the prediction, and it's squared. And the last thing I want to do is I want to take the average. So I have in my equation, I add them all up and divide them by n, and then take the square root. So I can use this expression that I have here, where I type in equal square root average, and then I'm going to select the column G for my first model. So I need two parentheses to close. And I'm going to do the same thing with my next model, equal square root of the average, parentheses, and I'm going to type in the column H, close the parentheses, and that's it. So here what we can see, we have calculated the root mean squared error of both models, where one has an error of 265,000, the other is 256,000. So model 2 is my best model. Now, what's the interpretation of the root mean squared error? I'm going to mention this, but this is not accurate. The root mean squared error is approximately, but not exactly, your average error in price prediction. So basically, in average, we have an error of $256,000. But that is not 100% true. That's not exactly what root mean squared error is, but it's an interpretation. Now, you would consider, well, 256,000 is a huge error, especially when you have properties that are about $200,000. And you would be right. But the reason is because we're only using year built, bathrooms, and square footage to predict home prices. So if we were to use other parameters, what other features of the house would you use to make the prediction? So please type in the chat, what other ideas would you like to include into the model to make it even better? All right, seasonality. Yep, that is definitely parameters that you want to include. Nearby amenities, absolutely. What time of the year, number of bedrooms. Yeah, those are exactly right. So I'm going to switch from the spreadsheet. We're going to go back into our PowerPoint as we're wrapping up our hour. And what I mentioned is there has to be other considerations that you want to take into your model. So you all have mentioned several of them. Here's a list that is just a small slice of what you could continuously include in your model. So for example, you have what property type it is. So for example, is it a condo, a townhouse, etc. So if you can imagine an apartment and a house that have the same square footage, same number of bathrooms, and built in the same year, they might have very different prices. Has the house had renovations? Does it have a view? So we saw property with a view to the Space Needle. How are the school districts or the crime rate in the area? All those things are going to affect the property price. Does it have a hot tub, a pool, tennis courts? Does it have stairs, an elevator? Is it just a single floor? What are the interest rates from the banks? So even things that are not even part of the property themselves are going to affect the price. Somebody mentioned seasonality as well. Typically summer months, I think there's more property sold than in winter months, and so on. Does it have air conditioning or heating, parking included, laundry, what type of floors it has, what are the HOA fees, etc. So if you could include all of these parameters into your model, it is just going to get better and better. And then you have to think about other things that you might not be able to extract information. So for example, maybe the person selling the house is desperate to sell them because they need to sell it due to an emergency. They need the cash immediately, and they might be willing to take a lower price if the sale happens quicker. Or maybe they can wait for a better offer and they can sit around. Now, if we've covered the basics of linear regression. If you want to dive deeper into this, here's just a list of a lot of topics that are going to improve your linear regression model. These are concepts you would need to understand, like overfitting, underfitting, train, test, and validation splits, regularization, assumptions, collinearity, how to work with categorical features and feature normalization, etc. Again, this is just to mention that there is a lot more to learn about linear regression. And as I wrap things up before we go to the Q&A, I just want to mention a little bit about Scholar U, my company. We do trainings in technology and data for individuals, corporate trainings, and universities. We have on-demand courses, live online, and in-person courses. We cover all these topics that you see here, from Excel and Google Sheets and Python, exploratory data analysis, regression models, etc. And if you're interested in learning more about what we covered today, which is Excel or Google Sheets or linear regression, which is in a probability and statistics course, we have these 3 courses available on demand on our website here. And for the next hour, we do have a discount coupon. So I think we're almost up to time. If there's any questions, we can answer them via the chat. Okay, somebody's asking about the website. Let's see. Yeah, let's see if that link worked for you. I'm also in LinkedIn, so you can find me there. Feel free to connect. And I also have a YouTube channel. I publish videos frequently about topics like this. So feel free also to follow that. There you can subscribe for free and find all of this. So the question is, probability and statistics course similar to what we will share today. So the probability, it's a probability and statistics using spreadsheets. One of the chapters is on linear regression, and we do work with home price predictions. So one section of that course will include linear regression and using spreadsheets. Okay, and yeah, somebody made a comment that to go into the website, yeah, apparently you need to add the www at the beginning. If not, it didn't pull up.